Okay, now we will discuss surface integrals. First, we talked about line integrals already, but with line integrals, we integrate over a curve. And with surface integrals, we will integrate over a surface. Excuse me. Okay, so here's our surface, say, and we're going to take these little patches to approximate the surface. So we'll call that the patch. And we're going to evaluate our function at a point in the patch. I'll say each patch because we're going to do it for the whole surface. And then we're going to multiply it by the area of the patch. So let's let this be the axes. So from here, we're going to take the point okay, then we're going to take the limit as the size of the patch goes to 0. Of all of the patches. And delta S is the size of, or the area of the patch. And that's going to equal the surface integral. Okay, that's right. And that's the definition of surface integral. Okay, well, what does this have to do with anything? One example is that if S is the shape of a metal sheet and the density is described by f, the function, then the surface integral, when you evaluate it, will give you the mass of the sheet. So there's one use for this. Now, on our patch, so let's say we have a rectangle down here, and this is delta x, and this is delta y, and then our patch is up here. Excuse me. And let's say we're going to approximate that area by A cross B. Okay, that's A and this is B. Now, let's let this point and this point. Let's just do A. A is going to be delta x I, okay, because you're going to multiply delta x is here, so that's going to determine the x component plus okay, let's say this. So the kth component is going to be g of xi plus delta xi minus g of xi. say y, j. K, because that's going to be the difference in that. So if you add this vector with this vector, okay, let's say delta x is here, and we'll see delta x is down here. Delta x, that's the x component, and the y component is the difference in the functions that gets you from this point to this point, this point to this point. And this right here is approximately the derivative of g times delta x. All you do is divide that by delta x and take the limit, and you have the derivative with respect to g. So a is the vector delta x 0 gx delta x, and b is the vector 0 the same way, delta y g of y delta y. And when you cross them, you get the area, and take the magnitude, you get the area of the patch. That's going to be I, J, K, delta x, 0, G, x, delta x, 0, delta y, G, y, delta y. Well, that's going to be minus. And it says delta x. So when you take the magnitude, that's going to be the square root of gx squared plus g with respect to y squared plus 1 dx dy, which is dA. We'll note it as dA. dA is dx dy. So this is the approximate area of delta S, which is the area of the tangent patch, let's just say that. So the surface integral in this case is going to be the double integral over the domain D in the xy plane of f of xy, g of xy, square root of gx squared plus gy squared plus 1 dA. D is in the xy plane, and that gets carried to the surface S, and then you have the patch, and then you have the tangent plane on top of it. So there's the patch, it's hard to draw, and there's the tangent patch, and you add them all up, add the areas of all that up, and you get the surface integral to be that. Okay, if the surface is represented by parametric equations, or has a vector equation, RUV is x of UV, y of UV, z of UV, then delta S is RU cross RV, delta U delta V, and then the surface integral becomes this. The double integral over the domain. The UV is in the XY plane, or the UV plane. So this is the area of the tangent patch, and this is the height. Okay, let's talk about surface integrals involving a vector function f. Okay, and the explanation behind this is that suppose S is some kind of surface submerged in fluid, and the fluid's moving. So F is a velocity vector field. And ds is a small patch of area on S, and let's suppose F is continuous, then the amount of fluid I can erase that. Crossing or passing over ds in a unit of time is approximately equal to the volume of the cylinder of base area ds, and height is the scalar projection f dotted with n, the normal vector. Okay, let me draw a picture. And cylinder is used here in the general word. It's not just a can. Okay, so it's a general cylinder. Here's S. Here's the patch on S. The normal vector's pointing up, or however it goes. It doesn't always have to point straight up, but it's positive orientation, so N will point up. F, let's say, is here, and so our cylinder looks something like that in 3D. So that's just a little piece of the fluid that's passing across ds. So dV is going to be the volume of that cylinder, which is height times the area of the base. Okay, again, this is called the cylinder. Height times the area of the base. So the height is F dotted with N, and the area of the base is ds. So the double integral over the surface, this is the surface integral, is the amount, it's the total amount, because you're adding up all those cylinders. And it has a special name. This is called the flux of F, flux of F through the surface S. And that's equal to the surface integral of F over S, which is SF dotted with ds. Those are the same. And you can read about more of that in your text. Okay, again, if S is represented by a function, then the normal vector is going to be this. Okay, again, okay, here's your patch. Let's say A is that, B is that, and your normal vector is going to be A cross B over the magnitude of A cross B because it's a unit. This is the unit normal vector. The length is 1. Okay, and then we'll get a simpler formula for this. We'll let F be the vector valued function with the components P, Q, and R. Then the surface integral of F is, these are the same, and that's equal to PQR dotted with the normal vector, which is and ds, this is n, is the square root of f of x squared plus f of y squared plus 1 dA, and those cancel. So we have the double integral over d of minus p times f of x minus q times f of y plus r dotted with 1 dA. And that's if the surface has positive orientation. That means the normal vectors are going outward. Up or outward. And then you add a negative if it's negative orientation. Okay, let's try some of the homework problems.